Hi, my name is Tobi. Thank you all for coming to see my presentation. So today I will talk to you about InlineTypes. So of course the necessary disclaimers. So a bit about myself. I'm a developer on the OpenJ9 runtime team in Canada. In the past I've worked on runtime support for features like Lambda expressions and nestmates. I'm also a part of the Valhalla expert group, where the focus is on topics like InlineTypes. So to begin, I'll first talk about some of the challenges that exist today with the Java platform, most specifically the Java type system, and why it doesn't allow us to get the most out of our hardware. Then I'll introduce InlineTypes and show how InlineTypes can solve some of these challenges. So in the last 10 to 15 years, one of the biggest challenges to modern CPU performance has been memory latency. There are many cases where CPUs can process data much faster than they can receive it. Modern CPUs have fairly large caches to mitigate this problem, but this is about 8 megabytes on consumer laptops, and it can go as large as 120 megabytes on server chips. But even with these advancements, memory is still the bottleneck in most applications. Applications themselves are also getting larger. So being efficient with memory, in many cases, is the key to good performance. Here is a simple architectural diagram of a computer system with a NUMA memory layout. NUMA meaning non-uniform memory access. So in modern CPU architectures, CPUs are often grouped into nodes, and nodes are joined by an interconnection socket. The total RAM is divided between the nodes, so that each node has a local RAM and a remote RAM. Access to the remote RAM is done through the interconnection socket. This is why there is a non-uniform access. So in this example, we have two nodes, node 0, node 1. Each node has 4 CPUs. Each CPU has an L1 and L2 cache and an L3 cache shared between all the CPUs in the node. And the RAM is split evenly between the two nodes. So here are some latency numbers from a Core i7 5500 series. So it's a fairly old processor now, but the relative differences are pretty much the same. All of these numbers represent the optimistic case. So, for example, the L3 numbers, there's a range. I picked the smallest value. So in the leftmost column, we see the types of memory, registers being at the top. So these are basically the smallest one, and at the bottom is SSD I/O, which is the largest memory. In the second column are the sizes. The third column shows the latency in nanoseconds. So as you can see, with register access, it's essentially one cycle, one CPU cycle. With L1, it's about 4 cycles at 1.2 nanoseconds, and L2 it gets larger, L3 it gets even larger. And then there's a bit of a jump when you get to RAM. And then after that, an SSD, it's a few orders of magnitude larger. On the rightmost column is a scaled version, just to provide a more human interpretation of these numbers. So as you can see, the smaller the memory, the faster the access. The larger the memory, the slower the access. So what this table shows is that it pays to have condensed data where temporal and spatial locality are aligned. So what this means is that you want the data that you'll access together to be stored together. As soon as you have to move up to a higher tier of memory, then you will incur a higher latency cost. So it's very important to have condensed data. One of the great things about the Java language is identity. Identity is useful because it lets you keep track of state. In Java, every object has identity. So if its state mutates, it still remains the same object. This is very appealing for software developers, which is why object-oriented languages like Java have become as popular as they are. And it means that you can perform identity operations on any object. However, there are some cases where you don't need the identity of an object. The value does not mutate, or you're simply using an object as a data carrier. So in these cases, you don't actually need identity, but you still have to pay the cost of identity. And as we'll see in the following slides, this cost can be very large. So one of the biggest challenges in dealing with identity are references. In order to maintain a single view of an object's state, you need to have a reference to that object so that everyone can point to the same thing. As a result, references are everywhere in the JVM. When the JVM allocates an object, it returns a reference to that object. And when the object is pushed onto the stack, it's a reference to that object that's pushed onto the stack. If an object has reference fields, then you get more references. And for types like hash table, which contains an object array, there are even more references. Each element of the array is actually a reference to where that element is stored. And then, in the case of hash table, the elements have references as well. So this, you end up with more and more references. And eventually, you end up with a large object graph that we're all familiar with. So it's easy to see how references can take up a large proportion of the Java heap's footprint. One of the problems with references is that there's a lot of pointer chasing involved. In order to access an object, you have to dereference the pointer. If you want to access a deeply nested object, then you have to dereference each of the pointers leading up to it. Depending on where that pointer is, it might be a relatively fast or slow access. So for example, in this case, library and hash table are in L1 cache, so dereferencing books is not too expensive. However, dereferencing table will be noticeably slower, as table is not in L1, it's in L2. So if you recall the chart showed earlier, L2 is about 4 times slower than L1. So dereferencing table will be noticeably slower than it was to dereference books. Likewise, dereferencing the first entry in the array will incur an even larger latency cost since it has to go all the way to L3. You can construct a similar scenario with NUMA nodes. Going through the interconnection socket will be slower than if the memory was in the same node. And with pages as well, if you have a page fault, if you're unfortunate enough to have a page fault while the application is running, you'll incur a very large latency cost, as disk I/O is many orders of magnitude slower than memory. So this makes things like serialization very expensive, as you need to traverse the object graph in order to acquire the application state. This involves making a lot of dependent loads that cross cache, NUMA, and page boundaries. So to summarize, references can result in poor locality. Another great feature of Java is synchronization, as it lets you get a consistent view of the same data in parallel processing applications. Synchronization is becoming more important because computers are getting more cores. So it's in order to make use of these cores, we're doing more things in parallel. So synchronization is very important. In order to support the locking mechanisms, JVMs often add a lock word to the header of the object. The problem is, in Java, every object can be locked on, even if you have no intention on acquiring a lock on that object. This means that every object has a lock word in its header. This is typically 32 bits in a compressed refs JVM mode. So this adds to the overhead. The cost of headers and references is really obvious when you're looking at arrays. Java has 2 types of arrays. One is a reference array, and the other is a primitive array. So on the left is a reference array, an object array. So the body of an object array has references that points to the elements, whereas with primitive arrays, the body contains the elements. With primitive arrays, you have a much more compact layout, which is better, but you're limited to the 8 primitive types. With object arrays, you can have any kind of object array, but you do have indirections. So the two main overheads are references and headers. If we look at an object array, we can see that these overheads really add up. For every element you have one reference and you have a header. So if we were to compare a Java-like integer array, for example, an int is only 32 bits. So for every integer you have one reference, so one word-sized value, and you have a header. So this means that for every byte of data, you have 2 bytes of overhead. If you were using a 64-bit JVM, it would be for every byte of data, you have 4 bytes of overhead. So as you can see that, there's a big cost to having indirections. This starts to make up a very large proportion of the footprints of the Java heap. And this is just for managing references. So this makes it very difficult to get the data that's related to fit in the same cache line because you have all the extra bloats. And that assumes that they were allocated closely together in the first place. There are some things that garbage collectors do in order to fix locality problems. They attempt to move objects that are accessed together, closer together based on access patterns, but these are not always guaranteed. So one of the features of modern hardware is that it attempts to prefetch memory based on your access pattern. So this means that if you're doing a sequential access, the CPU can prefetch the cache lines that you will need so that by the time you get there, they're already in the cache and you don't have a high latency cost for the memory fetch. This is shown to greatly improve performance in CPU architectures from Haswell and later. Comparing sequential to random access is about 60% faster on these architectures. So it's a very nice hardware optimization. And one of the ways to take advantage of this in Java is by using primitive arrays, because you have a contiguous layout. However, with object arrays, we're not as fortunate. In reality, they look more like this. There is no guarantee that the array elements are actually allocated in order. So in reality, they're really random. So even though you are accessing each array element sequentially, you're essentially doing random accesses in memory. So you get no benefit from hardware prefetch. Typically, garbage collectors in the JVM function by finding all the live objects and then removing everything else. The process of finding live objects is called marking. And this process begins by traversing the root set. So the root set is things like static fields, JNI, references, references on the stack. So the GC uses the root set to find all the live objects. So in this case, we can see that the GC looks at all the references on the stack, and it uses this to traverse the object graph. So as you can see, the more references you have, the longer it will take for the GC to find all the objects. If we compare scanning an object array with a primitive array, you can see that it's much faster to scan a primitive array because all the elements are in the array body. So as soon as you reach the header of the primitive array, you're essentially at a terminal point. You don't have to continue. But with a reference array, you have to scan each of the elements. So you can see that this, having more references, it increases the GC overhead. There are a lot of things garbage collectors now do to minimize the cost, like segmenting the heap into different regions, or performing marking concurrently. But generally speaking, the fewer references you have, the less of a GC overhead you'll get. So JVMs also have just-in-time compilers. A JIT is a dynamic compiler that compiles the JVM bytecodes into machine code. It performs many optimizations on bytecodes to improve performance. And one of the things that JITs like to do is they like to avoid object allocations. So as we've seen earlier, if you allocate something on the heap, you need to provide a reference to it. So if you can avoid the allocation by either stack allocating it or leaving it in registers, then your performance will be a lot better. So in order to do this kind of optimization, the JIT has to perform escape analysis to determine if the value will only be accessed by a single thread in its lifetime. If that's the case, then the JIT can stack allocate it or simply leave it in registers for even better performance. In this example, foo is allocated, then a method is called on foo, and the method returns. So in this case, the compiler can look at foo, look at the constructor, see what's going on, see if the instance will actually escape. It can look at getBar, do the same thing. And so it's very easy to determine if foo escapes. And if it doesn't escape, then the compiler can simply stack allocate foo or leave it in registers. So this is a very simple example, and it's very easy to determine in this case. But in reality, it's a very hard problem for compilers to solve. If we look at bar, for example, the third line where bar is returned, if we want to know if bar escapes, we need to know what the caller of this method is going to do with it. So if this method is inlined into the caller, then it's easier for the compiler to determine if it escapes or not, because the compiler has a much broader view of what's going on. But if the compiler cannot prove that bar is not going to escape, then it has to allocate it on the heap. And then we end up with all the drawbacks of references. So the reason why this is hard is because of identity. Because objects have identity, you have to track it at all times, just in case someone might perform an operation that requires identity, or that exposes the identity of an object. So identity is the very big cost, and this is shown in terms of references and the header overheads. So here's a recap of the challenges with Java today. There are too many references. References are everywhere. There's a lot of pointer chasing involved, and increases the likelihood of cache misses. Out-of-line object arrays are really inefficient. It's a very inefficient layout. Also causes cache misses. And it also doesn't allow you to benefit from hardware optimizations like prefetching. And due to references being everywhere, there's a lot of overhead associated with headers. And due to identity, it's hard for compilers to stack allocate. So we need a solution. And the solution is InlineTypes. So InlineTypes are essentially objects that behave like primitives. Hence the tagline, codes like a class, works like an int. InlineTypes is a new Java feature planned for a future JDK release. So it's not currently released. It's still under development. It's part of Project Valhalla. And it's something that will come out in the future. Now I'll talk a bit more about the roadmap later on. If you are familiar with value types, this is the same thing. InlineTypes are a new name. This was recently changed this past year. So if you've heard of value types, then you know what I'm talking about. And just as a disclaimer, what I will describe in this presentation is basically the current state of InlineTypes. This project is still under development, so things are changing very quickly. And in a few weeks, things may have changed again. So I'll describe the core concepts, where we're coming from, and where we're likely going. So the main characteristics of InlineTypes are that they are immutable, identityless, and most importantly, flattenable. Immutability means that an instance of an inline type does not change once it's been created. So if you want to change an inline type, you have to create a new one. Identityless means that an inline type, which has the same contents as another inline type, is indistinguishable from each other. So if it has the same values, they are the same. And as a result, identity operations like locking are not permitted. Flattenable means that the JVM is free to embed or inline an inline type within its container. So inline types can be embedded in arrays or in fields of singleton types. So as you can see, inline types have a lot of the same characteristics as primitive types. Primitive types don't have identity. Int of 1 is the same everywhere. Primitive types are embedded within their containers, and they're immutable. So they're very similar in that respect. So here is a little illustration. Let's say we define point with two integer fields, x and y, and we define line with 2 point fields, start and end. The layout would look something like this. So this is what we're currently familiar with. We have two references in line, and they point to 2 point fields. But if point is converted to an inline type, it looks more like this. So we can see that instead of having two references, the point fields are embedded within the line. So this means better cache locality, better footprint. We've saved two references and two headers, and better optimizations. So this is a big improvement. So if we look at the right, what has changed? Well, we've added the inline keyword to point. This gives the point class the flattenable, immutable, and identityless characteristics. So yeah, we can construct a similar example with arrays. So here is the typical Java array. Each element is a reference to where that element actually is stored. But with an inline array, all the elements are stored inline. So it looks more like a primitive array. So you have a flattened representation, less indirection, and this can take advantage of hardware prefetch if you're doing a sequential access. So again, this is a very big improvement. So a little bit of history before I continue. MVT, minimal value types. This was the first inline type prototype. Back then, it was still called value types. With this prototype, the only way users could use inline types was with method handles or generated bytecodes. So it was there was no Java C support. It was really intended for people who are really familiar with bytecodes. What this prototype demonstrated is that inline types can provide very good performance. But it did expose a lot of the user issues. In this prototype, inline types did not subclass Java-lang object, so it was very difficult for inline types to be used with existing APIs. In this model, inline types are queue types, so they had separate bytecodes. Much like primitives, primitives today have separate bytecodes, and in order to call a function on primitives, you have to box the primitive. So the same was true with inline types in the MVT prototype. So in the MVT model, inline types are essentially user-defined primitives. They have all the benefits and all the drawbacks of primitives. The next prototype was LW1. In this model, inline types are a subclass of Java-lang object. So in this model, they become more like restricted objects. They use the same bytecodes as regular objects, and you can call methods on them. So this is a very big improvement from a usability perspective. However, there are still some issues identifying how to expose nullability or determining which places you can flatten inline types. So the next prototype was LW2, LWorld 2, which is the latest version, and it answers a lot of those questions. Much of what I'll describe today is based on LW2 and some of the more recent discussion in the expert group. So we already know that inline types are immutable, flattenable, and identityless. But aside from that, they're just like regular classes. This means you can define methods, you can implement interfaces. So these are things you can't do with primitives today. They subclass Java-lang objects, so they have things like equals, toString, hash code. But as we'll see later, their behavior is different because these types are identityless. So by unifying inline types with objects, this makes it a lot more usable. But as you'll see later, this poses a challenge for the JVM. This increases the complexity that the JVM has to deal with. So inline types are great because they allow users to define data aggregates that the JVM can easily optimize. However, there are some trade-offs when using inline types. You get improved performance, but by definition, you have to give up some functionality. They are essentially restricted objects. So inline types cannot be subclassed. Since inline types may be flattened, a subclass can add more fields, which means that the flattened representation would have a variable size layout. So for this reason, they can't be subclassed. And since inline types are identityless, you can't perform identity operations like acquiring a monitor or synchronizing on them. They don't implement clonable because for an identityless type, there is really no point of cloning it. They can't be enums, since enums contain identity and enums are mutable. And similarly, they can't define finalizers. Finalization is a mechanism related to identity. Finalizers run when an instance dies, but inline types don't have identity, so they don't die. So for this reason, you can't define finalizers. So, as previously mentioned a few times now, inline types are flattenable, which means they can be embedded in their containers, as we saw in the earlier examples. So as a consequence of this, a flattenable field cannot be null, so inline types are not nullable. When a field is flattened, all the bits are used to represent data, so there is no way to represent null. So this is why they're not nullable. Also, inline types cannot have instance fields that refer to themselves either directly or indirectly. It's impossible to determine the layout of a flattened structure that is recursively defined. So for this reason, you can't do that. And because the size of an instance needs to be known at class load time, you have to preload all the flattenable types during class loading. So this is a bit of a change in the class loading mechanisms. Typically, you only preload the super types and super interfaces, but with inline types, you also have to load the flattenable types. So the three previous points kind of list the requirements or restrictions of flattenability, but at the end of the day, it's the JVM that decides whether a field is flattened or not. Generally speaking, it's better to flatten, but if a type gets too large, it might not be beneficial. You might actually get worse performance by flattening. So for this reason, the JVM makes the final decision on whether a field is flattened or not. So let's take a look at how inline types fit with the rest of the Java world. So here's the hierarchy. At the top, we have JavaLang object and inline types subclass from JavaLang object. Like it's the same as reference types. And you also have interfaces, so inline classes can subclass interfaces. Because of this hierarchy, inline types can be used everywhere references can be used. So this is very good for usability. Off to the side are primitives. Primitives don't have the same interoperability with references. This is why there's a lot of boxing involved when you're trying to use primitives with APIs. So this is one of the benefits of inline types, because you get the usability of reference types with the performance of primitive types. So here is the inline type hierarchy. At the top is object, and then in the middle is a nullable inline type, followed by the inline type. So in the previous slides, we talked about flattening and the performance benefits of flattening that can be gained. But we also looked at some of the restrictions associated with flattening fields. There may be cases where users don't want to flatten an inline type because they want to define a recursive structure, like a linked list node, or they want the ability to write null, or they may just want an indirection. In these cases, users can create a nullable inline type. So the LW2 syntax is the question mark. So what this means is that the container can contain an inline type or null. So as a result, the JVM will not flatten that container, and you can recursively you can have a recursive definition with this nullable type. So you can't actually instantiate a nullable inline type. A nullable inline type literally means an inline type or null. So it's the value set of the inline type and null. So casting from, in this case, casting from point to a point question mark is a no-op, and casting the other way around will perform a null check. Arrays have a similar hierarchy. The object array is at the top, followed by the nullable inline type array, and then the inline type array. So this hierarchy means that arrays are covariant. This is different from how primitive arrays are dealt with. Primitive arrays do not subclass object array, so they're kept separate. But with inline type arrays do subclass object arrays. So they can be used where in APIs that accept object array. So these are the higher level characteristics of inline types. Now we'll look at some of the details. So as you know, Java source code is compiled by Javac and produces a Java class file that contains what the JVM needs to know about the class. Inline types are distinguished by an ACC value type class modifier. So it's a bit set in the class modifier that lets the JVM know that it's an inline type. Inline types are mutable, so all the fields are implicitly made final, even if you specify it or not in the source code. And the final in this case means basically what it does with regular fields, except it's more tightly enforced. So things like setAccessible cannot write a final field with inline types. The class is also marked as final because it can't be subclassed. Inline types also don't have constructors. They have factory methods. So they have a static initializer. Also, the flattened fields have Q signatures instead of L signatures. So this lets the JVM distinguish between things that are flattenable and things that aren't. The same is true for method parameters and return types, in case the JVM wants to scalarize arguments for method invocations. So now let's look at how the JVM deals with them. So there are two new bytecodes introduced for inline types. The first is default value. Default value behaves a lot like the new bytecode. It creates a new inline type and initializes all the fields to the default values. So for primitives, this is 0. For references, this is null. The key difference between default value and new is that it doesn't require initialization. As soon as an inline type is created with default value, it's already initialized. The with field bytecode takes an existing inline type and creates a new inline type with an updated value. So it doesn't change the value, it creates a new one. So let's take look at an example. So on the right is a factory method that would create points. So it looks a lot like the regular code that you would normally write. And in the middle is what Javac would generate. So as you can see, it's a static init, and it returns a Q point. So unlike with normal objects, we don't have to do the new dup init sequence. We just do default value, and we get an initialized inline type. So the first step, we run the default value bytecode, which creates an inline type. And in this case, all the values will be zeroed. So you may have noticed that this inline type is actually stored out of line. JVM can stack allocate this inline type, but it's still yet to be determined how beneficial it is to stack allocate in this case. There's nothing stopping the JVM to do this, but more research is still being done to see if buffering inline types in this particular situation is beneficial. So the next thing is to load the first parameter. So that's the iLoad 0. And then once the first parameter is loaded onto the stack, the with field bytecode takes the parameter and creates a new inline type with the updated field. So notice that the address changed. It's a different inline type than what we had before. And then we simply repeat the sequence for the next field. And the with field updates the value, and now we have it basically created our inline type. So this looks like a tedious sequence. For every field you want to set, you have to create a new inline type. In reality, the JIT will optimize this sequence so that it can just create the inline type in one go. So you don't have to create a new inline type for each field you want to set. So here are some of the other bytecode changes. So these are existing bytecodes, but their behavior is different because of inline types. The if acomp bytecodes are used for branching. these bytecodes, today these bytecodes simply do a reference comparison because comparisons with references are based on identity. So if the references are the same, then they're the same. But with inline types, since there is no identity, you have to do a structural comparison. You actually have to check if each field is the same. So this is a big difference between references and inline types. The put field, put static, and array store bytecodes can now throw null pointer exceptions if you attempt to write null into a inline type or inline type array. So this is something that they haven't done before. And if you attempt to update an inline type with put field, you'll get an exception as well, and legal access exception. The monitor enter and monitor exit bytecodes will throw exceptions if they're performed on inline types. And a check cast will throw a null pointer exception if it's casted to an inline type. There are also bytecodes that have to be modified to detect the storage of an inline type. Since inline types can be flattened, you have to know what size they are. Currently, reference types are always reference sized, so these bytecodes don't need to know anything about the type. They can assume that they're dealing with something that's reference sized. But with inline types, more work needs to be done. If the JVM chooses to buffer inline types, then the A-load, A-store, A-return bytecodes will have to be aware of this. Likewise, the array bytecodes have to be aware of the element size if the inline type is flattened. And the same thing for the array creation bytecodes. The get fields, get statics, the put fields, put statics also have to know the size for the same reasons. And if the JVM decides to registerize arguments and returns for inline types, then the invocation bytecodes also need to know. So because of these changes, there's more complexity in the JVM when dealing with inline types. Today, these bytecodes are very simple because you're only dealing with references. But with inline types, there's a lot more complexity, and there's a lot more work for the JVM to optimize these things as well as they are today. There are some API changes. A new reflective call is added to class to query if it's an inline type or not. Identity methods like javlang object will now throw exceptions if they're performed on an inline type. And equals will perform a substitutability test by default for inline types. The hash code of an inline type is based on its contents rather than identity. So if two inline types with the same contents will produce this same hash code. And that's mostly it for the details. But now we'll take a look at some of the caveats of using inline types. So here's an example. If you allocate an array of reference types today, when you allocate the array, it'll be filled with nulls. So if you have, this is a very contrived example, but if you have code, you allocate an array, then the if null will be true because there's nothing in the array. But with inline types, because they are not nullable, when you allocate an array, they're not null. They're filled with values. So the logic here is different. And this is something that might be surprising to users, that I don't have nulls anymore. If you're depending on this, then you might have some issues in your code. So this is something that users need to be aware of when dealing with inline types. Here's another example. It's likely going to be more common. But there are APIs out there that accept types like javlang object or object array. Today, all references are nullable. So a lot of APIs will assume that if it's a subclass of object, you can write null to it. But as soon as inline types are introduced, this will cause issues. In method 1 over here, you could potentially get a null pointer exception if what you're dealing with is an inline array, is an inline type array. So in these cases, there might be some challenges for users who are not aware of the changes here. There's some things that Java C can do to help you out. If the static type is an inline type, then JavaC or even the IDE can let you know that you're making a mistake. But if the static type is not an inline type, then only runtime exceptions will notify you of this issue. The same is true as well for synchronization. So you can construct a very similar example with synchronization. If you synchronize on something that has a static type of object, you might potentially get an exception if it's an inline type. So these are some things that might be surprising to users. There are some other potential surprises if you're not careful with your data types. And in this example, we have an inline class node. It has a nullable inline type next field. So the way equality comparisons work with inline types is that you have to check, you have to do a structural comparison. So you're not doing a reference comparison, you're checking each field. And so if the field is a primitive, then you perform a primitive comparison. If the field is a reference that cannot contain an inline type, you perform an identity comparison. But if the field is a reference that can contain an inline type, like objects or interface or the nullable inline type, then you have to recursively perform the substitutability test again. So if we had two nodes that were equivalent, if these nodes were very large, or if these nodes had a cycle, then it would take you forever to return true, essentially. So these are things that, developers are probably not used to today because equality comparisons are very fast right now. In fact, they're one of the fastest operations that you can do. But with inline types, these operations could take potentially a long time. So it's another thing to be careful with. Because inline types are subclasses of object array, it means that one can pass a flattened array as an object array. So flattened arrays are nice because they have a very compact layout. But it is a challenge for the JIT. Today, if the static type is a reference type, the JIT can very easily generate code to access the array because it knows the element width of the array. In this case, we have an object array. If inline types were introduced in this JDK, the JIT would actually have a hard time optimizing this because it doesn't know the size of the element. It could be any size because an inline type can now subclass arrays. So this is something that requires more engineering, more optimization for the compilers in order to make this as performant as it is today. So from a user perspective, the best case is to actually have the most specific type. If the static type here was an inline type, then the JIT can statically know exactly what the element width is and then generate performant code as it does today. Currently, there's no support for inline types over generics for the same reason that there's no support for primitives over generics. Once Java supports specialized generics, then inline types will be supported with generics. So as a result, if you want to use an inline type with generics, you have to box them. So by boxing them, you essentially have to use the nullable inline type. So with the LW2 syntax, you simply provide the question mark, and it uses the nullable inline type. Inline arrays behave a lot like primitive arrays. This means that an array field is a reference. So the inline arrays are not themselves inlined within your container. They're still stored as an indirection. There's a separate project that's investigating these sort of arrays. It's called Arrays 2.0. So this sort of layout where you have a variable-sized array within a container is not part of the scope of Project Valhalla. So tearing is an issue that arises when a processor cannot write a value atomically. So in this case, if the processor doesn't have large enough registers, it writes a value with it in multiple writes. If you have contention, so if you have multiple threads trying to write to the same memory location, without any synchronization, it's possible to end up with a value that is half written by each thread. So the JVM spec today guarantees that 32-bit values or smaller will not tear. In reality, this is 64 bits because with 64-bit JVMs, there are plenty of registers that can atomically write 64 bits. And in today's world, the largest primitive is 64 bits, and references are 64 bits. So tearing is not really an issue that Java developers have to deal with. But with flattened types, it's not inconceivable to get types that are 128 bits or even 256 bits. So in this case, if you have contended writes, it'll become more likely that you'll observe tearing if there isn't any explicit synchronization blocking this. So this is something that will likely, in the future release, there'll likely be some modifiers that users can specify in order to, so that the JVM can be aware of the intentions of the programmer, so that if they do want to guarantee atomicity, then either if the JVM does not have a register large enough to do an atomic write, it will decide to not flatten the value, in which case you're back to a reference and the JVM can deal with that atomically. So a lot of progress has been made in this project, but there are still some key questions. One of them is, what should inline type boxes be? So should they be nullable inline types? From a syntactic perspective, how should they be represented in the language? LW2 represents them as a question mark, but they could easily be point.ref or point.box or something else. But more importantly, how should they be? What should their implementation be? Should they be interfaces? Should they be abstract classes? And also, should nullable inline types be used to denote indirection and nullability, or should these characteristics be dealt with separately? So these are things that are being discussed. Also, what should the Java type system look like? Because InlineTypes subclass JavaLang object, users will need a way to know if they're dealing with an inline type or not. In the examples we saw earlier, if you're not aware of what you're dealing with, then you can get a lot of runtime exceptions. So one way of solving this is by expanding the type system and providing two new sort of top types, one for inline types, one for reference types. And with this distinction, the ACC value bit will not be necessary. You can simply look at the supertype to know if you're dealing with inline type. And this will let users kind of segment their code in such a way that they can avoid some of the pitfalls we saw earlier. Then, should these types be interfaces or abstract classes? Abstract classes are nice because they let inline types define behavior by simply overriding, and so all inline types get that behavior. But kind of replacing all existing superclasses with ref object will be very difficult, as there's a lot of code out there that does these kind of checks and expects to see JavaLang object. So these are some of the things that are still being looked at. Another one is value-based classes. How will these be migrated? Value-based classes are classes that exist today. These classes don't make use of identity characteristics. They're created by factories, and all the fields are final. So these are classes that would be inline types if inline types existed in JDK 8. So the problem is these types can still be assigned null, and inline types cannot be. So migrating these types will be a challenge. So this is something that's still being investigated. So where are valid types going? So right now we're somewhere between LW3 and LW10. The examples that I showed you earlier are based on LW2. And the design challenges that were just discussed are things that will have to be determined before LW10. LW10 is going to be the first official production-ready release. So at this point, all of those design challenges will have been solved. LW20 will add support for migrating value-based classes, and LW100 will add support for specialized generics. So at this point, Valhalla will be complete. So there isn't really a timeline, unfortunately, right now, but it is coming. So stay tuned for that. So to summarize, with inline types, there are fewer interactions, and this is because you have inline object arrays and inline fields, and it's easier for JITs to stack allocate because inline types don't have identity. So this makes World a much better place and Java performance a lot better. So this concludes my talk. Thank you all for listening.
Thanks.